reaction mechanisms, rate law, and the rate limiting step. When we write chemical reactions, we are representing the entire process from the beginning to the end, and we're ignoring about all the details that occur in the middle. Let's imagine this chemical reaction. We have nitrogen monoxide reaction with hydrogen gas to form water and nitrogen gas. If you think about that and you think about the actual particles involved, I think it's pretty easy to see that it's unlikely that that reaction all occurs in one step. 2 of those particles and 2 of those particles, so 4 particles meet in one location at one time with enough energy. It just doesn't make a lot of sense. What instead we can consider is maybe the reaction occurs in a number of smaller steps, which we don't really observe because they either happen quickly or slowly, but then very quickly it gets all the way from what we see at the beginning to what we see at the end, and we can ignore the pathway in which it occurred. Here's a chemical reaction. Here's one proposed mechanism for this chemical reaction. Imagine the 2 NOs find each other and they form N2O2. Then that N2O2 finds hydrogen, forms NO2 and H2O, and then that N2O finds another hydrogen, forms N2 and H2O. I think you can see that this is a much more plausible way for this reaction to get all the way from here to here in a number of steps, those steps being a little more reasonable. So then the question becomes, if this is what's happening, which of these steps are the ones that are the rate limiting step, or the one that's causing the reaction to be slowed down? Typically with these types of reactions, there'll be some reactions which occur quickly and some reactions which occur slowly. Let's imagine that this occurred fast, and this occurs very fast, but this reaction right here occurs slowly. Why would one rate limiting step occur more slowly than the other ones? Well, there's 2 basic factors to consider. Remember, we're always talking about having collisions, and in those collisions having enough energy. So, if these steps involve different amounts of change in chemical potential energy, so let's say, as I've done it here, this first step only requires a little change, and then the second step has a much bigger activation energy, and then the third step has some other activation energy before it goes back down to the product level. The step with the highest activation energy is the most likely step to be the rate limiting step. I think this is straightforward. If collisions occur in that step because the activation energy is large, it's less likely for them to have enough energy, and so here we get fewer effective collisions leading to the formation of that activated complex, and so that slows down that step's ability to happen. Keeping in mind that we should be considering absolute amounts here. So if we had something like this, where it went up and then came back down, and then it only went up a little bit more and then came back down, this activation energy is bigger than this activation energy, so this is the step that would be more likely to be the rate limiting step. So it's not an absolute maximum chemical potential energy, but instead it's the relative changes. See, this change is bigger than this change is bigger than this change, and so it's the absolute change that would affect whether or not it's the rate limiting step, or it's the change, not the absolute amount. The second thing that can lead to something being the rate limiting step is if a complex collision involving 3 or more particles is required. The more particles that are required to be at the collision site, the less likely that effective collisions will happen. So, a rate limiting step might be the rate limiting step because it requires 3 or more particles to be in the same point at the same time, creating a very unlikely collision. So here we can see this one has 2 and this one has 2, so based on what I've said, this one must have a higher activation energy, and that's what's slowing it down. Now with that in mind, the way we think about this is almost imagine an assembly line where you're building bicycles. maybe putting the wheels on is really fast and putting the handlebars on is really fast, but once you get those wheels on, you got to put that chain on, and that's a finicky, frustrating step. And so you can imagine if you have 3 guys building bicycles, one guy's putting tires on them and it's going really, really fast. And on the other end, the guy's going to put the handlebars on, it's going to go really, really fast. But products are piling up at that step, or bicycles are piling up at that step where you're putting the chain on. That's what's sort of the slowdown of the whole process. The rate law uses the rate limiting step to predict which concentration of reactants will affect the overall rate of reaction. If we have a rate limiting step of A species A and B species B going to whatever, then the rate law says that the rate will be proportional to the concentration of species A to the exponent A and the concentration of B to the exponent B. In the rate law, we only include initial reactants. So let's see what that rate law would look like for our specific reaction up here. This is our rate limiting step. And so we're just looking for reactants available in the overall reaction. So the only one here we're looking at is H2. So our rate would be proportional to the concentration of H2 to the power 1. See, it has a 1 coefficient on it in here. It's H2, and I do not include the concentration of N2O2 because it is not an initial reactant. Just looking at another example, let's say I had A2 plus 2B is going to form 2AB. And I learned that this happens by 2B's becoming B2 in a slow step, and then A2 plus B2 becoming A2B2, and A2 and B2 splitting into 2AB. Since this is slow and these are fast, this one would be the rate limiting step. And if I wanted to write my reaction or my rate law for this, I would say that my rate is proportional to my reactant B. But since I have a coefficient of 2 here, I would expect it to be a second order relationship, or related to B squared. So reactions come in many steps. They don't all happen at once from beginning to end, but they're individual processes. Typically, one of these processes will be slower than the other processes. This process might be slower because of a high activation energy, or it might be slow because of an unlikely collision. Either way, we can use the rate limiting step to predict the relationship between the rate and the concentration of the individual reactants. We take reactants that were in the overall equation and we set them to the exponent of their coefficient in the rate limiting step. For example here, 2B's, so B squared. Or for example here, 1H2, so H2 to the power 1. And then we can determine, or we can predict, how changing the concentration of one of the reactants will numerically affect the actual reaction rate. Finally, the overall order of the reaction, which depends on the number of particles that need to come together to come up with a collision, can be found by finding the total of the exponents in the rate law. If we said rate, for example, in some other reaction we haven't made up yet, was related to A to the power 1 and B to the power of 2, we would say that 3 particles need to come together to make this reaction happen. So we would call this an order 3 reaction. order 1 reaction, order 2 reactions are common. Third order reactions are uncommon. Fourth order reactions, I think you'd be hard pressed to find a lot of real world examples where fourth order reactions happen. Having 4 particles in the same place in the same time is just really unlikely. So that's what rate laws, rate mechanisms, and order of reactions are.